Students, welcome to Yupp Master, the school foundation program. So, today what we are going to discuss is very important concept. Already we have started that one in the previous class. We are discussing about the isomerism introduction part, and then let us move on to the isomerism that we can see in the case of alkanes. Okay. So, yesterday we have defined the isomerism and we have seen the different types of isomerism with respect to the structural as well as stereoisomerism, and we were stopped exactly at the structural isomerism. We are discussing the different types of structural isomerisms. Okay. So, isomerism, it is a phenomenon where two or more compounds having the same chemical formula will exhibit different physical and chemical properties. Okay. So, isomerism is two types, structural isomerism as well as stereoisomerism. Structural isomerism we were discussing in structural isomerism we have writing the different types, or we are discussing the different types of structural isomerisms. Yesterday we have discussed the chain isomerism and as well as the positional isomerism. Okay. Chain isomerism, positional isomerism we have discussed. What is chain isomerism? Chain isomerism is that in which the compounds, two or more organic compounds will have the same chemical formula, but the arrangement of carbon atoms is different. Chain isomerism we can see in the case of hydrocarbons, especially alkanes, alkenes, alkynes, etc. And in the case of positional isomerism, yesterday we have defined the positional isomerism. So, these are the compounds, organic compounds having the same chemical formula, but there will be a different in the position of the functional group, or position of the double bond, or position of a triple bond, or even we can take the substituent presence at different positions. Okay. So, let us take one more example with respect to the positional isomerism, where we are going to deal with the corresponding alkenes molecule. For example, if you take CH3, CH2, CH, double bond CH2. So, if you observe the double bond position, here the double bond is present in between the first and second carbon atoms. Okay. So, if we can write one more isomer in this case as CH3, CH double bond CH, CH3. So, if you observe here the double bond, now the position of the double bond, if you observe, it is between second carbon and third carbon. In the first case, the double bond is between first and second carbon atoms. So, it is between first and second carbon atom the double bond is present. In the second case, between second and third carbon the double bond is present. So, when you observe the position of the double bond, in this case it is between these two, in other case it is between these two. So, here the position of the double bond is different. We have the same length, 4 carbons are present in the straight chain, but there is a change in the position of the double bond. So, these two can be considered as positional isomers. Okay. Right. We can also categorize the structural isomerism as functional group isomerism. One more is functional group isomerism. What is functional group isomerism, and where the functional group isomerism is, the compounds are going to differ. So, these are the compounds which are having the same chemical formula. So, I am not writing the same chemical formula. Okay. So, I am just writing the difference where we are going to come across in this kind of isomers. So, in this case particularly the compounds will differ in the functional groups. Okay. So, the functional group that is present in organic compound will decide the isomerism here. Okay. So, these are the compounds which are going to have the same chemical formula, but they are going to have different functional groups. Okay. What is functional group? An atom or a group of atoms which are attached to a carbon chain will decide its characteristic properties. That group or that atom of group of atoms is taken as a functional group. Okay. So, these are the isomers in which the compounds will have the same chemical formula, but they have different functional groups. When they have different functional groups, then they are going to exhibit this functional group isomerism. For example, if you write this one, alcohols and ethers. Alcohols and ethers are the best examples which are going to show the functional group isomerism. Okay. Right. For suppose here in this case if you take the examples of functional group isomers, alcohols and ethers are functional isomers of one another. For suppose, let me write the example so that you can understand. Let us take ethyl alcohol, CH3, CH2, OH, ethyl alcohol, okay, ROH is alcohol functionality. Ether you can write as dimethyl ether, that is CH3O, CH3 is ether. So this is different functional group and this is different functional group. This ROH is taken as alcohol, ROR is taken as ether, okay. So in this case if you observe, does the two compound will have the same chemical formula? Just look at the number of carbon atoms. So we have 2 carbon atoms, 6 hydrogen atoms and 1 oxygen atom in this case, okay. So this is I have written in a bracket, right. Look at the ether compound as well, CH3O, CH3. So here if you observe, we have 2 carbons, 6 hydrogens and 1 oxygen. So here if you observe, in case of CH3O, CH3 also we have the same formula. So both are having the same chemical formula, but what is the difference? They are exhibiting different properties because of the different functional groups. Here we have ROH, this is alcohol. Here we have ROR, so this is ether. So alcohols and ethers are functional isomers of one another. So simply we can remember that functional isomerism is the organic compounds which are having the same chemical formula, but they differ, they have different functional groups. They will differ in the functional group present in the molecule, okay. So that is how we can categorize or we can define the functional group isomerism, okay. The phenomenon is taken as isomerism and these two compounds are taken as functional group isomers, okay. Organic compound, the compounds which are exhibiting that isomerism are called as isomers. Since it is the functional group isomerism, so these are two are functional isomers, okay, right. Coming to the next different type of structural isomerism, metamerism. What do you mean by metamerism? So generally metamerism is observed in the case of the organic functional groups which are bifunctional in nature, okay. Generally it can be observed in bifunctional groups, okay. What do you mean by bifunctional? The functional group is going to have both sides the alkyl groups, okay. In other words, we can define this as metamerism, the organic compounds having the same chemical formula, but they differ in the alkyl chain length, on either side of the functional group, on either side of functional group. On either side of the functional group, the number of carbon atoms present is different. So that is how they are going to give us the isomers, and that isomer, those isomers are called as metamers, and that phenomenon is known as metamerism. Metamerism is organic compounds having same chemical formula, but they differ in the alkyl chain length on either side of the functional groups. So therefore only bifunctional moieties are going to exhibit this metamerism. Especially we can see in the case of ethers as well as in the case of ketones, okay. So when you observe the metamerism, so if you see the ethers, let us say in case of ethers is a bifunctional group, even ketones can be taken as bifunctional groups, okay. So ethers, if I take CH3, CH2O, CH2, CH3. So this is a bifunctional group which has 2 alkyl groups. This side we have 1 alkyl group and that side we have 1 alkyl group. If we observe here, we have 2 carbon atoms on this side, okay. If you observe here, we have 2 carbon atoms. So 2 carbon atoms are present on either side of the oxygen, okay, in this molecule. If I write the one more molecule CH3O, CH2, CH2, CH3. If we observe this example, this side we have only 1 carbon atom, okay. If you observe this side, we have 3 carbon atoms. In first case, in either side of the oxygen atom, two carbons are present. In the next example which I have given, here one side we have 1 carbon atom, this side we have 3 carbon atoms. So the carbon atoms are different on either side of the functional group. Only the alkyl groups, alkyl length will be, alkyl chain length will be different on either side of the functional group, and these two can be taken as metamers, and the phenomenon is known as metamerism. So if you observe here, the if I write the chemical formula of this compound, 2 carbons, total 4 carbons, so C carbon is taken 4 times. If I observe the hydrogen, this side we have 5 hydrogen, this side we have 5 hydrogens, so total number of hydrogens are 10, so it is H10 and 1 oxygen atom, so I am writing it as oxygen. Okay. So this is the chemical formula of the first compound. Look at the chemical formula of the second compound. So here if you observe, this side we have 1 carbon atom and this side we have 3 carbon atoms. So 1 plus 3, 4 carbons are present. If you look at the number of hydrogen atoms, here we have 3 hydrogens, here we have 7, 7 plus 3, 10. So 10 hydrogen atoms are present, and if you observe here we have 1 oxygen atom. So C4H10O is the formula of this compound, and this compound formula is also C4H10O. What is the difference you can find here? Around the functional group, the different chain length is present. In first case, on either side of the oxygen we have 2 carbons, only 2 carbon this side, 2 carbon this side. Okay. In the second case, I am writing in such a way that one side I am taking only 1 carbon atom, other side I am taking 3 carbons. So if you observe the, of course they are ethers only, both these compounds are ethers only, but there is a difference in the alkyl chain that is present on either side of the oxygen atom, and thereby they exhibit isomerism. That isomerism is called as metamerism. Okay, right. And we have one more isomerism under structural isomerism, that is tautomerism. Tautomerism. So here tautomers generally they differ, they will have the same chemical formula, but they differ in hydrogen, that is proton, as well as the electrons in the molecule. The arrangement of hydrogen, the proton as well as the electrons are different in this particular compounds, and thereby they exhibit isomerism, that is taken as tautomerism. Generally the most famous is keto-enol tautomerism. Keto-enol tautomerism. For example, if I take acetone, CH3CO CH3, propanone, that is ketone. Okay. So here I can write the arrangement, one of the hydrogen can move from here on to the oxygen atom, and thereby we get a COH double bond CH2. So if we observe here we have a keto group, so it is called as keto isomer. Okay, this is keto, C double bond O is taken as keto, R COOR. Okay, and in this case if we observe we have CH3 C double bond CH2, here we have a double bond, therefore it is taken as ene. Double bond presence is indicated with the ene, as we are indicating the saturation present with ane, alkane. So we are indicating the double bond with the ene, and one OH group is present, alcohol group, so we write it as ol. Okay, it is enol, so therefore it is enol, and this is keto group. So keto-enol tautomerism can be seen with respect to, if you observe here there is a difference in the arrangement of the hydrogen atom and the movement of electrons. So electron movement is, and the proton arrangement is different in this particular two compounds. Both are having the same number of carbon atoms, same number of hydrogen atoms. If I observe the number of carbon atoms, total 3 carbons are present. How many hydrogens? 6 hydrogens and 1 oxygen. So if I observe here, the formula of this compound is C3H6O. Here if you observe here also the same formula is present. So they are going to have the same chemical formula, but they differ in the proton and the electron arrangement, and thereby they exhibit isomerism. Here bond breaking and bond formation takes place in this particular isomerism, that is keto-enol isomerism. Okay, and we have one more structural isomerism. We can come across one more structural isomerism, that is ring chain isomerism. Ring chain isomerism. What is ring chain isomerism? The name itself indicating us one compound will be in ring form, that is cyclic form, one will be in a straight chain fashion. Okay. So, here the compounds will have the same chemical formula, they differ. One compound will be in a cyclic fashion, okay, whereas another compound or another organic compound will be in a open chain fashion, open chain compound. Okay. So, here if you take the best example that we come across, alkenes and cycloalkanes, cycloalkanes are best examples which are going to exhibit ring chain isomerism. For suppose if I write propene CH3 CH double bond CH2. So, this is alkene, one double bond is present, it is an alkene. We have discussed the alkanes, alkenes and alkynes functional group presence when we are dealing the classification of organic compounds in the previous classes, right. So, here the presence of a double bond between the two carbon atoms, it is an alkene, propene. So, if I write the cycloalkane, cyclopropane, it is a triangle shape with the CH2s on the corners of a triangle. So, if we observe the formula, in this case the formula is C3H6. Here also if we observe cyclopropane, it is C3H6. 3 carbons are present, total hydrogens are 6. Here also if we observe 3 carbons present, hydrogen number is 6. So, one is open chain compound, other is a ring or cyclic compound. So, these two alkenes and cycloalkanes exhibit ring chain isomerism. Compounds will have the same chemical formula, but one compound will be in cyclic fashion, another compound will be in open chain fashion, and thereby they exhibit ring chain isomerism. So, these are the different types of structural isomerism that we come across in case of structural isomerism classification. Okay. So, first one is chain, second one is positional isomerism, third one is functional group isomerism, okay, and fourth one if you see, fourth one is metamerism, okay, and the fifth one you can take the tautomerism, and the last one you can take as ring chain isomerism. So, these many different types of structural isomerisms are possible in case of organic compounds. We will come across again when we are dealing the what do you call these haloalkanes and alcohols, ether, carboxylic acids, carbonyl compounds, etc. We will come across these isomerisms again in the different topics of organic chemistry. Okay. Now, let us move on to the next stereo isomerism. In case of stereoisomerism, as we have discussed, what is stereoisomerism? These are the organic compounds having the same chemical formula, but there will be a difference in the spatial orientation of the atoms attached in a 3-dimensional space around the central atom, and thereby we get two different types of isomerisms. One is geometrical isomerism, okay, geometrical isomerism. What is the geometrical isomerism? These are the compounds having the same chemical formula, same chemical connectivity, connectivity will also remain the same. What is the difference we come across in this case? We can see that the orientation of the groups will be different. Generally, this is observed in the case of compounds which are having restricted rotation. Geometrical isomerism generally observed in the case of compounds having restricted rotation. Generally, the carbon-carbon double bond, carbon-nitrogen double bond or nitrogen-nitrogen double bond, there will be a rotation around this carbon-carbon, carbon-nitrogen, nitrogen-nitrogen is restricted because of the presence of the double bond, that is pi bonds, okay, and thereby the rotation is not possible. Because of the restricted rotation, the groups will orient specifically around the 3-dimensional space around the molecule, and thereby we are going to get the isomerism. Geometrical isomerism is also termed as cis-trans isomerism, cis-trans isomerism. Let me take an example so that you can clearly observe how the groups are going to be oriented in the space because of the restricted rotation. For suppose we have a carbon-carbon double bond on which one side we have HCH3, other side also we have HCH3. 2-butene is the best example that we can see. Okay. So, in this case I can write the same molecule again in a different orientation. You can just observe here. So, carbon-carbon double bond, one carbon attached with the hydrogen and CH3, other side I am taking the CH3 little upside and downside the hydrogen. So, this is also 2-butene. What is the difference between these two compounds? Yes, if you observe here the methyl CH3 on this carbon and CH3 on the other carbon are on the same side of the double bond. They are orienting toward the same side, and hydrogens are orienting the same side. So, when the groups, similar groups are oriented in same side of the double bond, then that compound is said to be cis isomer. The compound is said to be a cis isomer. And if you observe the second example, this is 2-butene, but the methyl group on one carbon is towards downside, and the other side this carbon, the methyl group is present on the upside. So, if you observe, the similar groups are oriented on opposite sides of the double bond. Similar groups are oriented on the opposite side of the double bond. So, you observe here the hydrogens are also oriented on opposite side of the double bond. So, this molecule is known as trans isomer. So, cis and trans isomer existence is taken as geometrical isomerism. So, if you observe the connectivity in this case, the connectivity is also same, the chemical formula is also same, but only the thing that the difference in this case in these two compounds is that the similar groups in one case are oriented on the same side, in other case they are oriented on the opposite side of the double bond, and thereby the isomers are going to form here. So, these two are called as geometrical isomers. So, alkenes will exhibit the geometrical isomers, azo compounds will exhibit the geometrical isomers, imine compounds will also exhibit the geometrical isomers. When we move into the detailed discussion of alkenes, we will come across the different types of cis and trans orientations and different examples. Okay. So, this is how they are going to be formed. So, the geometrical isomers are obtained because of the restricted rotation, and these are the isomers which are going to have the same chemical formula, same chemical connectivity, but only the orientation of the groups are different. Okay, right. Coming to the other side. So, the other side we can write the stereoisomerism as optical isomers or optical isomerism. One is geometrical isomerism, other is optical isomerism. Okay. So, what is optical isomerism? So, here the compounds going to have the same chemical formula, same connectivity, but the arrangement of groups in the 3-dimensional is different. Okay. Arrangement of groups in 3-dimensional space is different. Only they differ in the groups arrangement in 3 dimensions. Okay. So, thereby the compound is going to exhibit optical isomerism. So, what is the main condition for a molecule to exhibit optical isomerism is it should possess an asymmetric center. An asymmetric center presence is must. Okay. Asymmetric center is presence is must within the molecule to exhibit optical isomerism. Okay. For example, if we are going to look into the methane molecule having different bonds around it or the different groups arrangement, let us say in case of methane I am replacing 3 hydrogens with 1 iodine, 1 chloro and 1 bromo. If I am keeping this molecule in front of a mirror, I am going to get the mirror image. So if I write the mirror image, so I am going to get a bromine here, chloro this side, iodine the other side. Since bromine is present here, so bromine will come here in the case of mirror image. So if I take this compound, the mirror image, if I take the mirror image and if I make to coincide on this molecule, the groups will not coincide. So in other words, we can say that these are the two mirror images which are non-superimposable. Non-superimposable mirror images. These two are non-superimposable mirror images. If I take the mirror image and if I want to coincide with the original molecule, the bromine and iodine will collide with one another, bromine and iodine collide with one another. So the collision of the superimposable in this case is not possible, and thereby these two are non-superimposable mirror images of one another, and thereby this molecule is optically active. So here if I say that this molecule possesses an asymmetric center, so this molecule is optically active, and these two are known as optical isomers. Optical isomers. So here if I take how they are going to differ, since the compound having same chemical formula, same connectivity, where they are going to differ? They are going to differ in the rotation of plane polarized light. So when a plane polarized light is passed through these compounds, one compound will rotate the plane polarized light towards the right side, other compound will rotate the plane polarized light towards the left side. So the compound which rotates the plane polarized light towards the right side is always known as dextro compound. The compound which is going to rotate the plane polarized light towards the left side is known as levo compound. The compound which rotates the plane polarized light towards the right side is called as dextro-rotatory compound. Glucose is the best example. We call the glucose as dextrose because it rotates the plane polarized light towards the right side. Fructose is the best example. We call it as a levo sugar. Levo means it is going to rotate the plane polarized light towards the left side. So the compound which rotates the plane polarized light towards the left side is known as levo-rotatory compound, and the compound which rotates the plane polarized light toward the right side is called as dextro compound. So if we are going to have the optical isomers, one isomer will rotate the plane polarized light in one direction, and exactly the other isomer will rotate the plane polarized light in exactly the other direction. Okay, if one is rotating in right side means the other one rotate the plane polarized light towards the left side, and these optical isomers are generally known as enantiomers. Optical isomers are generally called as enantiomers in this case. Okay. So of course we will come across again all these concepts when we are dealing the haloalkanes as well as haloarenes. There we will come across in detail discussion about this optical isomerism and how the compounds are going to be differ in their properties. These are the compounds having the same chemical formula, same chemical connectivity, but the orientation of the groups in three-dimensional space around the central atom is different, and thereby one rotate the plane polarized light in one direction, other rotate the plane polarized light in other direction, and thereby they will exhibit the optical isomerism, and these compounds are known as optical isomers. Okay, right. So in general, if you observe what we have discussed so far from last 2 days, if you observe, we have categorized the isomerism into structural isomerism as well as stereoisomerism. Okay, and within structural isomerism we have different branches. What are they? Chain isomerism, positional isomerism, okay, and functional group isomerism, and then we have seen the metamerism, okay, and then we have seen the tautomerism, and even we can consider the ring chain isomerism as the structural isomerism. So we have discussed these many different types of structural isomers, okay, and in this case In the case of stereo, we have come across the geometrical isomerism and optical isomerism. Okay. So this is how we can classify the isomerism into different categories. Structural isomerism, chain isomerism, positional isomerism, functional group isomerism, metamerism, tautomerism and ring chain isomerism. Stereo isomerism is geometrical isomerism, optical isomerism. We will come across all these things when we are dealing the different topics in organic chemistry. Don't worry, we will discuss all these things. Only in order to give you a brief introduction about the isomers, I have given, we have gone through the classification of isomerisms. But what we are going to discuss in the case of alkanes is this one, the chain isomerism. Okay, right. Let us look into the isomerism in alkanes. Right. Isomerism in alkane, if you observe in this case, as we have discussed, alkanes will exhibit only chain isomerism. Okay. So alkanes will exhibit only chain isomerism. Okay, because here we have its alkanes are saturated hydrocarbons and no unsaturation is present, no other functional groups are present, and thereby we cannot expect any positional isomerism or functional group isomerism or metamerism, etc. We can expect only the chain isomerism in the case of alkanes. So which compounds exhibit generally the chain isomerism? Chain isomerism can be seen or observed only in alkanes which are having 4 number of carbon atoms. From 4 number of carbon atoms we can observe the chain isomerism. So what about the first 3? Compound having only 1 carbon atom, that is methane, compound having 2 carbon atoms, that is ethane, compound having 3 carbon atoms, that is propane. If we observe, they do not exhibit any chain isomerism. Why? As we have discussed, what is chain isomerism? These are the isomers which are having same chemical formula. Where they differ? They differ in, where they are going to differ? They differ in carbon atom arrangement in the chain. Okay. Only the difference that we can see in the case of chain isomers is the carbon atom arrangement. The carbon atoms are going to be arranged in different fashion and thereby we can expect the chain isomerism. When we have only 1 carbon atom, we cannot arrange them, or when we have only 2 carbon atoms, we cannot arrange them in a different fashion. Only possibility 1 carbon, no other chance, only we can write this way. If we have 2 carbons, only this way, you cannot connect in other fashion. Okay. If we have 3 carbons, let me write this way. Okay, or if I take a CCC, of course both are same, these two are equal. So we cannot write or we cannot arrange the carbon atoms in different fashions in alkanes containing 1 carbon, 2 carbon, 3 carbons. So methane, ethane, propane, they won't show any chain isomers. Okay, we cannot expect any chain isomerism from carbon, methane, ethane, propane. Okay, these are the 3 alkanes which does not have any isomers. So we can see or we can observe the isomerism, chain isomerism from alkane having 4 carbon atoms. So from alkane which is going to have 4 carbon onwards, okay, alkanes from 4 carbon onwards, they will exhibit chain isomerism. So chain isomerism is possible in case of alkanes. So the minimum number of carbon atoms should present in the alkane is 4. Up to 3 carbons we cannot expect any chain isomerism. So what are the different chain isomers that are possible in the case of carbon having, alkane having 4 carbon atoms? What is the name of this compound? Whenever we have 4 carbon atoms, the alkane name is given as butane. Okay, right. So if we observe the butane, we can arrange the 4 carbons in a straight chain fashion, CH3, CH2, CH3. So this is normal butane. We are going to use the N, we have discussed. The N prefix is used in case when carbons are arranged in a straight chain and there is no branching. Okay, unbranched carbon chains are, we are going to use the N prefix. Okay, N indicates here it's a normal unbranched chain. Okay, so 4 carbons are arranged in a straight chain fashion. If I take one of the carbon atom, if I take this methyl group and if I attach to the one of the middle carbon, we get a CH3, CH, CH3, CH3. So here if we observe, I am taking one CH3 and attaching to the second carbon and thereby 3 carbons are present in a straight chain, 1 carbon I have taken it as a branch. Okay, 3 carbons are present in a straight chain, 1 carbon I have taken it as a branch. Okay, so now this compound if you observe, second last carbon atom in a chain, if it is going to have a methyl substituent, it is what kind of prefix we are going to use? Iso. So it is isobutane. So this is a zigzag fashion of representing and this is the complete writing the formula of the compound N-butane and this is isobutane. 3 carbons in a straight chain and 1 carbon as a substituent. Okay. So what could be the IUPAC names of these 2 compounds? We know that the 4 carbon chain, the IUPAC name is butane, there is no doubt. N-butane, it is normal naming system, common naming system. Okay, trivial naming system we are going to use N-butane. According to IUPAC we have to use butane, that is it, no need to mention N. Okay, and if you observe here, and if I am giving numbers to the carbon atoms after selecting the continuous carbon, longest carbon chain, it has 3 carbons. So if I number the carbon atoms such that the carbon having the substitution getting the lowest possible number, that is 2. So at second position we have a CH3, so we can write it as 2 methyl 3 carbon alkane chain is known as propane. 2 methyl propane is IUPAC name of this compound. Common name is isobutane. So we are going to use iso prefix when the second last carbon atom, if it is going to have a methyl group and no other substitutions are present on the parent chain, in that case iso prefix can be used. Okay, and if you write the IUPAC name, in case of IUPAC name you have to select the continuous longest carbon chain. Okay, and then number the carbon chain so that the substituted carbon should get the lowest possible number, and once you assign the numbering, then mention the substitutions first followed by the parent name. So substitution can be named by its position. You have to write the name of the substitution and also its position on the parent chain. At second position we have methyl, so I am writing it as 2 dash methyl propane is the name of the compound. Okay, so butane, how many chain isomers are possible in the case of butane? Only 2 chain isomers are possible. 2 chain isomers are possible for butane. Okay, if I take propane, pentane, in the case of pentane I can write the isomers. First I will write the straight chain, all the 5 carbons I am arranging in a straight chain. Okay, I will take 4 carbons in a straight chain and 1 substitution, 1 methyl as a substitution, or I will write 3 carbons in a straight chain, I will take 2 carbons as substitutions. So in this case we can arrange the 5 carbons in a straight chain, 4 carbons in a straight chain followed by 1 substitution, 3 carbons in straight chain by 2 substitutions. So here this one is called as N-pentane, normal pentane, where all the carbon atoms are present in a straight chain. This is called as isopentane. Why it is called as isopentane? So at the second last carbon atom, if we have a methyl group, according to the common naming system, iso prefix can be used. Total number of carbon atoms, if you observe, it is 5. So we are using the name as isopentane. And if you observe here, on the second last carbon atom, if 2 methyl groups are present, we use the prefix neo, and the total number of carbon atoms on the compound is 5. So we write it as neopentane. So pentane exhibit 3 chain isomers, one is N-pentane, other is isopentane, third one is neopentane. So if I write the IUPAC names of these compounds, so 5 carbons are arranged in a straight chain, so we can write it as pentane. But when you look at this one, 4 carbons in a straight chain, 1 substitution. So we have to select the longest continuous chain. So I am selecting the longest continuous chain which has 4 number of carbon atoms. Then number the carbon chain such that the substituted carbon gets the lowest possible number, it is second position. At second position we have a CH3, so we can write the isopentane IUPAC name as 2-methyl butane. What is the name? 2-methyl butane. We have selected the 4 carbon chain as a continuous carbon chain, so the alkane, parent alkane will be butane, and 1 substitution is present on the second carbon, so I am writing it as 2 hyphen alkyl name, here alkyl is CH3, so I am writing it as methyl, parent name is butane, so I am writing it as butane. So IUPAC name of isopentane is 2-methyl butane, 2-methyl butane. Right, coming to the neopentane, if you observe, so I am selecting the continuous carbon chain which has 3 carbon atoms. If you select in any direction, you are going to get only 3 carbon atoms as a continuous chain. So the parent chain is propane, 3 carbons are present, so it is a propane. But at second carbon we have 2 methyl groups. Okay, we have 2 methyl groups at the second carbon. So we can write it as 2, 2 dimethyl, 2, 2 dimethyl propane is the name of the compound. Neopentane name is, IUPAC name is 2, 2 dimethyl propane. At second position we have 2 methyl groups, so we are writing it as 2, 2. Whenever the same substituents are present, same alkyl groups are present, no need to mention them again and again, no need to write methyl, just use the term dimethyl. Where it is present, 2 methyls are present on second carbon and on second carbon. So I am writing it as 2, 2 hyphen dimethyl propane is the name of neopentane. Okay, right. So here if you observe pentane, how many chain isomers are possible? 3 chain isomers are possible in the case of pentane. What about hexane? In the case of hexane, we are going to have 5 chain isomers. What are they? I am writing in a zigzag fashion. Okay, so I can arrange all the 6 carbon atoms in a straight chain, or I can arrange 5 carbon atoms in a straight chain, 1 group as the substitution at the second position, or I will arrange the 5 carbons in a straight chain, substitution at the third carbon atom. Okay, similarly I can arrange the 4 carbons in a straight chain, 2 as substitutions at the second and third position, 4 carbons in a straight chain, I can arrange the 2 methyl or substitution at a first position. So total 5 isomers are possible in the case of hexane. Okay, so if I write the name of this one, what is IUPAC name of this compound? All the carbon atoms are arranged in a straight fashion, so we can write it as hexane. Okay, so if I number this compound by selecting the longest continuous carbon chain having 5 carbon atoms, at second position I have a methyl, so you can write it as 2-methyl pentane is the name of IUPAC name of this compound. Similarly in this case also, if I select the continuous carbon chain having 5 carbon atoms, so parent chain is pentane, but methyl substitution is present at the third position, so we can write it as 3-methyl pentane is the name of this compound. Okay, and if you observe this one, so if I select the continuous carbon chain having 4 carbon atoms, parent name is butane, at second position we have methyl, third position we have a methyl, so I can write it as 2, 3 dimethyl butane, 2, 3 dimethyl butane. And if I take this compound, at second position we have 2 methyls, so we can write it as 2, 2 dimethyl butane. Students, you have to arrange the carbon atoms and write the IUPAC names for the compound. So here if you observe hexane exhibiting 5 isomers. So similarly if you say for carbon, alkane having 7 carbon atoms, we can expect 9 isomers. Alkane having 8 carbons, we have 18 chain isomers. 9 carbons, we are going to get 35 isomers. If we have 10 carbon chain, that is decane, it is going to have 75 chain isomers. Okay. So, as the number of carbon atoms increases in alkane, the number of chain isomers also increasing. So, these things you have to keep it in mind and try to write the isomers that are possible for the hexane and heptane on your own, and try to write the IUPAC names according to the guidelines what we have discussed in the previous classes. So, students, it is easy to write the structures, isomers and the IUPAC names of the compounds. And we will see some more things about the isomers in the next class. Till then, have a nice time. Thank you.